Right, we'll start with some announcements. So we have an exam a week from today. Study guide will be out by the end of the day. I'm gonna try a slight experiment with this. In that instead of giving you a note card, I'm gonna give you a full sheet of paper. And I don't think the difference is going to be hugely meaningful. But that's kind of the experiment, is to see if things change, people have that much more space. So I'm very interested to find out, and I think it will be more useful, especially when there are a few more things to memorize, maybe. I don't think that's really the case, more so than necessary or usual, but we'll see. So page of notes front and back rather than a note card. Yep. I don't usually fully like doing open note, open book, but if there was any class where that would make sense, it would probably be this one. So I'm gonna start moving that direction and see what happens. Questions about the upcoming schedule before we get started on actually diving into compilers? All right, we will do that. I had half a slide at the very end of this last slide deck to go over. So we were talking about Turing machines and efficiency. So tying this back into some of the data structures and algorithms type analysis of the practicality of algorithms. So throughout this entire discussion, we talked about how Turing machines and the different types of Turing machines were equivalent. They were equivalent in terms of what they could compute. We completely ignored the concept of efficiency, how long it would take for these algorithms to terminate if they were going to terminate. So rather than go into a big deep dive on this, it's at least worth pointing out how you might analyze or see that these classes of Turing machines, well, they don't differ in the length, the kinds of languages they can accept. They very much differ in the computational complexity of setups that solve the same problem. So an example was, what is the efficiency of deciding A to the N, B to the N on a single tape Turing machine? Did we get this far? I already have the memory of a goldfish, I can't remember. So think about how you would construct a program for A to the N, B to the N on a single tape, and then think about how many transitions would you need with proportion to the length of the input? So what class of running time would we be in? For those of you who are walking slightly late, full page front and back of notes for the exam next week. You can use a note card if you'd like, but you can use a full page if you'd like to. Yeah, I only saw one of them at first, so I was like, oh, there's another one over there. It's like, yeah.
But n squared.
It is n squared. So you can think about, we're matching A's with B's. That's the way that we discussed solving the problem, is we match an A with a B. So how many transitions do we need? We need n skipping, or n over 2, I guess, skipping all the A's to match a B, and then n over 2 again to come back to the, if it's A to the N, B to the N, then there's n there and n back, because we have n A's. So 2n moves to match a single A with a single B and come back. And then how many of those do we have to match? We have n of them. So that leads to something like 2n squared, which is in order n squared. So we can think of this as a quadratic running time Turing machine. What happens if you can use 2 tapes? One assumption you need to make is the entire string starts on tape 1.
The method for doing it with 2 tapes.
So you could like move to the end of the A's. Start copying B's to the bottom tape. Assuming you have something like, if you can separate the heads, then you could. You could walk down the B's and copy them to the second tape. Then move back to the beginning and start matching A on tape 1 to B on tape 2, A on tape 1 to B on tape 2. Yeah,
Maybe, oh. Never mind, I had a train of thought and then it stopped because what do you call it?
Does it be linear then?
yeah, it does get to be linear. Why? What makes you think that?
I mean, the way I. Like my mind in the 2 heads, right, all of you, and all you have all of you go through and match and then.
Yeah,
I want to go through basically the entire string once.
yeah, and in fact, I said it the stupid way, going over all the A's. Copy all the A's to tape 2 first as you go, and then walk down the B's with the A's, and that way you don't even have to go back. It's the same order, but this is still faster. So the complexity of this is linear and not quadratic. So even though we said that Turing machines have the same power, language recognition power, again, we see that there are examples and very easy examples of you increase the. It isn't necessarily the power of the Turing machine, but you unlock some of those extra features that we were talking about, and we get to reduce the order of some problems. And what's interesting about this is I don't know if anyone in here has taken a parallel computing course, but this is, you can think of different tracks as different parallel algorithms or different options for parallelization. Question?
Spoken to something about, because I was trying to do it for like the homework, but I couldn't figure out how to do it or the language to do it, rather how to write it. Is there ways that you can have Turing machines separate the heads and make movement in a way, or is that something that's like?
Yeah, you just choose to move one and not the other. So it'd be something like, if you recognize here, you can do something like, if you include a stay as well, that one of them can stay and then one of them can move.
Okay,
And that way they detach, and you can just look at where the current position is with each of them as they move left or right or left or whatever, however they want to move. To me, it makes sense to just have a stay, because if you introduce a left or you keep it to a left or a right, then whenever you want to stay, it's just a left and followed by a right, or a right followed by a left. So it's trivial to introduce the concept of a stay. It just becomes, you take 2 transitions and make it 1 transition, but you end up needing an extra state to be able to say, whenever you go into this state, just go back the way you came and make no change. So it is an arbitrary complexity to the process in a way that doesn't really affect the design that I've had you go through when you answer questions about this. It just makes all the problems longer for no reason. So this speaks into the interest of parallelism. So the abstract parallel kind of goes back to Turing machines and Turing machines with extra tapes. So I just thought I'd point that out, if that helps you see parallelism in a different light now that we've studied Turing machines a little bit. That's kind of cool. If you have an algorithm and you can think of, what if I had multiple Turing machines for this algorithm and it ends up being in a simpler complexity, then maybe developing a parallel algorithm would be a good idea. So that's all I really wanted to say about this. Just wanted to make sure I got to it before we switch over to the next set of slides. All right, we finally have it all. We have all of the theory, all of the tools that we need to look at the process of compilation and be able to understand what's actually happening at each step. And not just at a very high level, but being able to look down at, what is this process? Why does it work? How does it, what logic do we use? What structures do we use? We can tie all of this back to things that we've covered so far in that course. So I had fun writing this. we're only at the end of week 7, coming up on week 8, and we're finally getting to talk about compilers, but let's just start. Yeah, that, I keep thinking there are 2 weeks left, 10 minus 2 is 8. We're finishing week 8, no, we're finishing week 7. We're finishing week 8, I think we're finishing week 7, but no, it's, yeah, 2 weeks left. Ah. All right, what is a compiler? What does it do?
Takes a programming language syntax and converts it into runnable.
Yeah, we're taking some kind of high level language, a Java, a Python, a C++, and we're converting it down into some low level language. This could be assembly, this could be straight to machine code. There are different possible outputs for this. You could be doing it into bytecode, which is kind of a similar to because we know that we have different architectures and the different architectures have different machine instructions and machine sets. So a bytecode is just one level above that, where everything can go directly to the bytecode, and then the bytecode is converted into each of those architectures. And that way you can have the same compilation process on all operating systems to get to that bytecode, and the only thing that changes is interpreting the bytecode into runnable machine code for that architecture. So at a very high level, a compiler is just translating high level code into assembly or machine code. We'll talk about compilation, and then we'll eventually come back and look at interpretation as well, because those are two that the most frequently used ways to convert. And they turn out to be similar, but very different. It's kind of a similar idea, but the way they go about it is very different. So getting an understanding of the difference between writing a compiler and writing an interpreter is useful. So we know high-level languages are easier for us to interact with. Has anyone written an assembly language program? How did that go? As soon as any program gets any kind of a little bit of complexity, then writing anything in assembly is just painful. So it's very nice that these high-level languages exist. We need something to bridge the gap between the raw logic of assembly language or assembly or machine code and the English type of logic that we use in our brains, or how our brains process information and how computers need to process information. So we invent these high-level languages that have a mapping to these low-level languages, so that we as programmers can work in the high-level language and we can still communicate with a computer. But somebody needs to write the translation such that the computer can understand the logic that we write. If we were to feed an actual CPU high-level code, it would think that it is gibberish. Just like the machine code that you look at is gibberish to you. Low-level languages, much harder to write, but they live in what computers understand. So we need some way of communicating. Note that if the target output language of a compiler is assembly, there's still an assembler that's going to convert it into machine code. I also talked about this, that machine code is platform dependent. So we have extensions that signify that something is in its associated machine code. So anything that's a .exe is just straight binary instructions. It's an executable. But have you ever tried to run an exe on a Mac system or on a Linux system? Does that work? No, the architectures are different. So because of this, to get to that stage, if the output isn't executable, then what you have is something that is Windows specific. So I also talked about bytecode a little bit. Rather than write a different compiler for each target architecture, we can invent a bytecode that is a middle ground. So we know that Java has Java bytecode. So when you compile Java, it doesn't go directly to machine code, it goes into bytecode. And then this is what makes Java so platform independent. That's its big benefit as a language, is that you can write a Java program And it will run on any operating system you attempt to run it on because of this bytecode system that has an easy conversion down into any particular architecture that you want to run it on. But the bytecode itself is platform independent. So the bytecode is run on a virtual machine. The virtual machine does that last step of converting it into machine code that runs on that machine. So let's start to think about this. If you were in charge of designing whatever process is needed to do this, what would you do? Before we reveal exactly what that process is and what steps there are, see what you can generate just based off of the logic of what needs to happen to convert that high level into low level. And then also thinking about maybe it uses some of the things that we've done this quarter. Or maybe it doesn't, and I've just been pulling your leg for the last 8 weeks. Just kidding, you're never going to use any of this. Yeah,
I guess you would have different things mapped to certain Java syntax would pretty much always map into a certain type of bytecode.
so
That's
just
good, how it
just
goes.
create the mapping of some kind.
Yeah. Although
How
it's
would that mapping be created? What would you do if you have as input just this long stream of characters that is a Java program or a Python program? Really all they are characters, right? How do you find meaning in this long list of characters?
make a grammar for.
The grammar in there somewhere? Are you ready to parse syntax immediately when you just have a stream of characters? How do we know that a particular section of a stream of characters is actually a terminal or is actually a non-terminal? What we assume when we write our grammar is that we have particular terminals and non-terminals, and when we've seen the application of this to programming languages, we assume that we have an easy way to map something like the word while to a terminal. We know that's a keyword in just about every language. So how do we know that? Context.
Yeah.
That would make sense. We need some way of producing what is the equivalent of the words in the language. So to go from this long stream of characters and identify that's a word, that's a terminal symbol, that's a word, that's white space, so we can ignore it. So we call that tokenizing. We write a scanner that's going to scan the input stream that is the program, character by character, and we need to break it apart into tokens. And those tokens are the terminals and non-terminals for the grammar. After this process is complete, what we have is no longer a stream of characters, but a stream of tokens. And each of those tokens map to something in the language that would be recognizable by a grammar. We then pass these tokens onto the parser. And the goal of the parser is to, using the grammar for the language, construct a parse tree out of this program. And the parse tree is basically going to be what are the derivations of the grammar that allow us to produce this program? And then you break that down so that you have the parts of the grammar, you produce the parse tree such that if you were to do a depth first search through this parse tree, you would be able to reconstruct your program. So the output to the parser step is a parse tree. That's fed into the type checker. The type checker is going to do the work that the grammar can't. This is what does the semantics analysis. Since the grammar can deal with the syntax, the type checker is going to make sure there aren't anything that's syntactically correct that is semantically meaningless or semantically incorrect. And the goal of the type checker, when applied to the parse tree, starts making what we call intermediate code. And the intermediate code, in order to generate that, you must have code that is both syntactically and semantically correct. So we go through and verify the semantics, and we go node by node through the parse tree, and we're going to be generating intermediate code at every node that we hit based on the rules of the grammar. The grammar is going to tell us how do we convert this into intermediate code. Once we have the intermediate code, we will be able to analyze that intermediate code and try to find any unnecessary slowness, or as I like to call it, unnecessary badness in your code. And then it will try to remove or get rid of or optimize parts of your code that can be optimized based on the output intermediate code, because faster code is better than slower code. And so you will find sometimes that you write code in a particularly inefficient way, but it doesn't actually affect the running time of your application. And that is because that is removed by a program that somebody else wrote. When you compile, there is an optimization process. After we produce a new batch of intermediate code that is an optimized version of the incoming intermediate code, we then spit this into the rules that generate the assembly or machine code at the very end of it. So these are the big sets of steps. So the remaining slides in this slide deck are going to go over each one of these steps in a little bit more detail. And then we are going to start to spend the next week or so zoomed in on what is the most difficult process of this whole thing, which is the parser. So the parser is going to be what we'll focus on for a while. And that's what I'm hoping to pull a project out of that I'll figure out this weekend. So tokens and scanning. We need a scanner. Again, this is the process of taking characters that we type and turning them into tokens that we can recognize as Java tokens or Python tokens. So these are the words of the language, the terminals and non-terminals as you would. So a token is just some number of characters surrounded by white space. We can think about that for now, but we're going to have to be cleverer than that, because if it were just that simple, we could write a program that was just a few lines and be able to tokenize. But you can think of anything that could be separated by white space as being a token. Sometimes programming languages don't force you to have that white space there, but if there could be white space there, then we will think of it as a token. Think about adding a space between something like an if and the open parentheses. If that doesn't break the syntax, then it's a different token. On the other hand, if we put a space between the I and the F in if, we're going to break the syntax. So those aren't separate tokens. After we do this process, we're going to assign each token a particular type that might represent the kind of variable it is, if it's a variable, whether or not it's a keyword, if we can recognize that token as a particular keyword, anything that we can know about this token, we will assign it that type. There's an extra process that needs to be done to handle this if the user hates white space. As an example, this is all one sequence of characters. This is all on one line. What are the tokens? 4 is a token. The open parentheses is a token. I is a token. Equals is a token. 0 is a token. Semicolon's a token. I less than 10, not just 1, but now I have to identify the 1 and the 0 as belonging to the same token. Semicolon. I
think
plus is a single plus is a single operator, so they go together. So you can imagine that when we set I, we could have had a plus in there. I equals 1 plus 1. And we'd have to be able to differentiate the 1 in that from coming from an expression and the plus plus as coming from an operator. So you can't just read the single plus and parse it the same way or tokenize it, I guess, the same way. We aren't even parsing yet. But we can't, there are more complicated rules underneath the hood here than you might first assume. When you just see, oh, I'm looking for tokens, and tokens are things that are separated by white space. The actual algorithmic process is a bit more difficult than that. So this is going to be stored as a long list of tuples. We're going to have the associated token and the type of the token, the label that we assign to that. We're going to pass that tuple list onto the parser in the order that they appeared in the program, and that gets us to the parsing step. So if we can crack this process, then we would be good. Note that very few programming languages allow you, or force you, sorry, to include white space where you need there to be white space separating tokens. So that means that the process doesn't actually increase the complexity much to be able to allow you to do that. So anything that you are allowed to do, you're allowed to do for a reason. And in this case, the reason is it's not that bad to figure that out. But we will eventually come back to this and talk about that actual process. Today, we're just doing a very high level of what is a compiler, what are the steps. So tokens and types, now we need a type associated with it. Let's start with the first line. Sum is a variable. Operator, yep. Total would be a variable. Plus would be an operator, 10 would be a constant.
Yeah.
How about the second one?
Green is a variable.
Variable,
If is a keyword.
yep.
6.5 is a
The float, constant. And 87 is an int constant.
yeah,
Sweet.
makes sense.
Is the top line syntactically correct in most languages? Is the, aside from, well, if it's Python, then you'd be fine. Is the bottom line syntactically correct in most languages? Maybe. Yeah, in a lot of languages it wouldn't be, but note that the tokens don't care. We're not even asking a question about syntax yet. We're just identifying tokens. We're not even asking the question, do these tokens make sense? Does the order of these tokens make sense? Does this have any meaning? None of those questions are being asked yet. So let's figure out, how could we do this? We'll give you the high level of how this is done for now, and then we'll come back to it in a bit more detail later. How could one implement a scanner? Anyone want to take a guess at things that we've seen so far this quarter? What would you use to implement a scanner?
State machine. Or
What kind of state machine?
one.
What would the associated language, if we're looking at Chomsky's hierarchy, what would the associated language be? What level of power would you need for your state machine? Would it be a finite state machine? Would it be a
Yeah, fine.
finite?
You probably only need a DFA for it, right? Because there's only a certain number of like.
That's exactly correct. You use a complicated DFA. And you're able to, based on the characters that you read, eventually associate them with something of meaning. Eventually, you'd have a final state that recognizes a particular keyword. If you see the character WHILE, then you'd end in a final state that says, this is a keyword. And then you start the next one back to the initial state, and you go until you recognize something or don't recognize it. And that would allow you to tokenize it into something. You would be able to say something like, this isn't a keyword, this isn't an integer constant, this isn't a float constant. It must be a variable. So final states recognize different types of tokens. We read in each token, until we have some set of characters that's identified as some kind of label of interest. We end in a final state and we're able to assign the associated label of the name of that state into the tuple, and then that allows us to do that. So now that we've talked about DFAs, we can understand the scanning process as just building a DFA and running a DFA for it. We can also build regular expressions for each valid token, since there was equivalence there. So we could either do this state by state with a DFA, or we could match to particular kinds of regular expressions. We'd have regular expressions that match all keywords, regular expressions that match all float types. Because we looked at this with one of our homework problems, right? How could you identify a floating point number? I think we did that with a bit of a grammar, but you could also do that with a regular expression as well. So that's the scanning process. Then we get to parsing, where we now have everything tokenized. So instead of getting in character by character, we're getting input that is token at a time. We have a context-free grammar that represents the associated programming language. There's a different grammar for every language. And the goal is to now, starting at some start state, figure out a sequence of productions to call from the starting state of the language's grammar to be able to produce this target program. So the parser's task is to derive the program from these tuples. So you apply production after production in the grammar. If the program can be derived, we have a syntactically correct program. If the grammar cannot be derived, there is a syntax error somewhere. And if you write this program intelligently, we can identify where that syntax error is. What part, how far did we get doing a left to right derivation of this before we could not finalize and come up with the associated chunk? Underline that as the place where the syntax error is occurring. So that's what your IDE is doing for you on the fly, is every second or so, it's just running through this parsing process, trying to produce what you've just typed out of the grammar of the language. And then if you have something that is not syntactically correct, it will underline it as it fails to find a way to go through and parse and produce this from the grammar. Over the course of this, we're building the parse tree. When we recognize what kind of production we need to apply at a particular place, then we make a note in the parse tree. Because we know now for sure that that rule is applied to produce this program. If our program has perfect syntax, then this process will complete. We'll be able to derive a complete parse tree such that if we did a depth first search of the parse tree, we would be able to reconstruct our program. If the program is not syntactically correct, then we need to do something that alerts the user that we have failure at this point. And back in the old day, you didn't have something like an IDE to run this. You actually ran the compiler. And so the errors that came back from the compiler would need to specifically state where the syntax error was. Like what line is it on, what, etc. And so what's happening is that is what's happening, but your IDE is interpreting that for you. It knows what line number and what character number and how long it is, so it can go underline it for you. But there's nothing that's actually different from that process. Finally, we send on the parse tree once it's derived and complete onto the type checker. Let's go over an example. We're going to have this interesting language. Every program has a main method, so this is not an object-oriented language, it's just a procedural language. Main method made up of a sequence of statements. Each of these statements must be an assignment or a print function. Nothing else. So here's an example program that is in this language. It's absolutely as simple as can be. We have a main. Then we have an assignment, and a print. Go ahead and write a context-free grammar for this language. You can use the following for your non-terminals. We can have program, sequence, line, variable, integer. Those are the only non-terminals that you will need, but try to construct the rules for this simple language using these non-terminals. It's the start non-terminal. Yes. So we're not having S or anything of the sort now. Program is the most abstracted idea out of your non-terminals, so we want to define what does every program have. Well, we know that every program starts with the main declaration. So the main and the open parentheses and the closed parentheses are all going to be terminals that appear in that first production. What follows main? Do we know any more terminals or anything more that we know comes in every program?
Oh. I don't know, I think a terminal would be the equal sign up.
Yeah, but not in this particular production, because nowhere in main is there an equals, but yeah, the equals is going to be a terminal in later productions.
Not really guaranteed anything in there.
Yeah, after main, we could have any assignment or print statement. So we're going to basically just say that that is sequence. There is something that comes after this, some number of lines. So we're just going to call that a sequence. So the very first line of this is basically program, arrow, main, open, close, sequence. And then we need to make another production that's going to define what sequence is. So sequence, arrow, what is a sequence made up of?
Line followed by sequence.
That would be one possibility.
Do we know what can be put in the print function? Because it seems like it's always something plus something else, or is it can be?
Oh, I missed one. Yeah, go ahead and put it, use an expression non-terminal. Yeah. Yeah, I missed one. Anyone think they have an answer? One person, I'll give you a little bit longer. Anyone feel like they're stuck? So how are we going to define sequence? What is a sequence?
I said a line or a line followed by another sequence.
Yeah. There are two possible ways. We could either have a sequence that is a single line, right, for any possible one-line program, or a line followed by a sequence. If we have more than one line, and that level of recursion allows us to be able to say with those two rules, programs of arbitrary length. It's either programs of a single line or programs of more than one line. How do we want to define line? Yeah,
I said a variable equal to like either a variable integer or expression, or like print with a variable integer expression.
you could certainly do that. I was assuming that all assignments are going to be, since we don't really have. We don't really have or need the complexity of something like a variable equals variable. There's no instance of that in the program, but you absolutely could include that in your grammar if you wanted to include that in the language. So variable equals variable, or variable equals integer, or what else did you say?
Variable equals expression.
Yeah, variable equals expression. Yeah, that would work. How about print? How are we including our print? Where does that show up in any of these non-terminals?
In the line.
Yeah, so we can also define line to, in addition to being what is this? Assignment, then it could also be a print statement. So here is one possible example. This just has the line equals variable equals integer. But we talked about a couple other possibilities there, but this would be some kind of reasonably fairly complete, very simple grammar for this very simple language. It doesn't do very much. But it at least shows you the kind of form that you might expect to be able to throw together programmatic syntax. Questions on any of this as an application of something that we talked about a while ago? Now think about going through and making a parse tree for this derivation. So think about now making a parse tree for this particular program. What would that look like going through? You can assume that we have this exact grammar. If you have more things in your grammar, that can be great, but we don't need all of those to be able to represent this particular program. Who remembers how to construct a parse tree? What do we do?
Do like main in the sequence and then sequence becomes like a line, the sequence and line sequence and.
Yeah, we're building a tree where each internal node represents some kind of non-terminal. And then we're gonna branch from there, producing terminals and non-terminals, and only non-terminals are going to be internal nodes, and terminals are going to be leaf nodes. This will get you started. And we are already out of time. So we'll come back to this and have an answer for this on Monday. Watch out for the study guide today. It'll be up sometime this afternoon, as soon as I have the ability to make it and put it on Canvas. That will allow you to get started studying for the exam. Since homework is due tonight, my goal will be to get that graded and back to you as soon as possible. I don't know exactly what that will look like yet, but at least within a couple days of the exam, that's my goal. Have a great weekend. See you on Monday.